Welcome to another coding session. I wanted to thank the people that watched the last series I made. In the beginning, I was not even sure if I was going to upload it at all. It was really rough. I basically just made it as a test, try out recording, try out uploading, and learn a few things. I didn't think I was actually going to upload it, but then I did, and I was really surprised. I thought no one was going to watch it. I thought I'd get like 3 views or something, but no, I got like a lot more views than I expected. At the time of recording, I have 95 subscribers. I'm really shocked by that. I was not expecting that. So I just want to say thanks. Yeah, and I hope you enjoy the series. So getting into it, we're making another compiler, this time for a more complex language, quite a low-level explicit language. For the most part, I don't want to do anything too fancy. The reason I like explicit, where the code that we write can map fairly directly to the assembly, is because I think it'll just be simpler to write that way, simpler to make the compiler. And also, I just have a preference for really explicit code. I like that. If there's too much implicit stuff going on, I feel like that's just, I don't know, in the end, frustrating, because you want to do something and you can't do it because you're stuck in this level up here. Anyway, and I do have a goal with this language. It's I guess you could say it's kind of a proof of concept. So I wanted to kind of draw out the idea. This is kind of the lofty goal, Along the way, we'll just do the normal kind of language stuff, build up a regular kind of language. But there is one kind of extra thing. Let me just stop this music. There is one extra thing that I wanted to add. One extra thing. Yeah, it's kind of my main motivation, actually. And that is that I want to be able to call or execute the code on the different hardware in the machine and store data in the different memory in the machine. So let me draw something to explain this a bit better. So we've got our CPU. I'm just going to make a box for this guy. So we've got our CPU sitting up here. And if I copy that and go down here, we've got our GPU. So I'm guessing most people know the difference between these. CPU is your central processing unit. That's where code that you normally write runs. GPU, usually used for games or AI these days, or other things where you need a lot of parallel processing. And typically at the moment, the way that you would access that is you would need to code in shading language, like GLSL, using OpenGL, Vulkan, or something along those lines. So, so those are the 2 places generally you can execute. I'm going to add in this guy as well, little baby GPU, because sometimes you can have integrated graphics. You have a CPU that has a little GPU in it, so it can do some graphics. It's not amazing. It's not going to be like a NVIDIA RTX, 5090 or whatever it is. At the time of recording, at least, that was kind of a new one. It's just going to be kind of basic-ish. But, you're definitely going to have a CPU. That CPU might have integrated graphics. And you might also have It's called a discrete GPU, which is when you have like your separate graphics card, which is usually the powerful one. So I guess those are the three main places you could execute code. Now I'm going to make a little box here, and I'm going to call it VRAM. Put him over there, and another box over here. And we're going to call this just RAM. So that's your memory. That's where you're going to store your data. So the reason I've positioned them here is because the CPU is very close to the RAM. The RAM is nice and fast for the CPU, and likewise the VRAM is nice and fast for the GPU. Now with the CPU, you can get your dirty little fingers over here and take a look at this VRAM, read it and write it, but it's going to be, it's my pencil, like this. This one here is going to be slow, this line here. So it's not ideal, you know, if you've got something that's executing on the CPU, then ideally you want the memory to be here because that's nice and fast. And you want to kind of limit this interaction because it's going to be slow. And then there's our little integrated GPU. Oops, let's go back to our other color. Our little integrated GPU over here. I said go back to the other color. Didn't I? Go like this. I don't know if you can hear the cat. He's whining, but he's not happy I'm giving him attention. Anyway, so this, because he's integrated, he's close to the RAM as well. And then I guess I could put another arrow kind of like this, but I'm going to put a big fat X on that one because as far as I'm aware, that's not possible. That GPU, he can only see his VRAM there. So why am I telling you all this stuff? So the idea of this language, because like I said before, the only way normally you can access the GPU is through a shading language, a separate language. So you have to write a separate little program in a separate language and then run a bunch of APIs to execute that program on the GPU. And my idea, let's see if it works or not, is, let's change our color. My idea is that if you have a procedure, and so let's, we'll do like a physics one. So we got like a position, which is a vec3, a velocity, which is a vec3, and then a delta time, which is a float. Oops, let's make this a bit bigger, hey? And then the idea with this is like to move forward our simulation, our physics simulation. The most basic thing you do is you go position plus equals velocity times delta time, something like that. Now, what I would like to do is, if we were to run this on the CPU normally, I should probably give this a name, shouldn't I? I'm going to do kind of, this is Odin-ish syntax because that's what I've been using recently, and that's what I'm going to code the compiler in. So even if you don't know Odin, you should be able to kind of, it's not too crazy. So we'll call this, I don't know, sim for physics sim or something. Or no, advance or update will do. Naming is hard. And then the update, to call it on the CPU, would just be something like this, and we'd pass in, you know, pos a, vel a, and delta, something like that. Very easy to call it on the CPU. And then what I would like to be able to do is I would just like to be able to go at GPU, and then it'll run on the GPU. This needs to be, like I said before, the GPU only can see VRAM. So we also need our POS data can be, an array of 1,000 vec3s at VRAM, something like that. And then we'd need to send the POS data into this. I'm simplifying things a lot, but I would like just to be able to say at this thing. That's what I would really like. I think that would be great. Again, I don't know how possible this is going to be. So let's see. That's why it's a proof of concept. I'm going to try it out. I think at least the initial implementation is going to be kind of hairy. I'm probably just going to go through OpenGL or Vulkan or something behind the scenes to make this work. And here, I'm saying just calling the function once. You would never do that. You would never just call a function once on the GPU. It would actually be more something like, I don't know, I was going to say, like, the idea I had was like hash bang, and then you pass in, the function you want to call, and then pos data and val data, and the delta is always the same. So I'm not actually sure how that would work because it's a scalar, whereas these are arrays, and then you would do that GPU. I don't know. I don't think we need to worry about this stuff right now because, yeah, like I said, this is kind of a goal for later. And at least to start with, we're just going to do regular, normal language stuff. Yeah, the reason that I bring this up now, at least at a high level, is because this is going to inform our decisions about like what language features do we want to add, because I want to prioritize the language features that will get us to this point. So there might be some language features that I might not even bother with, like if statements I might not even bother with because I don't really need them to get to here. But maybe at some point we feel like they'd be handy, and I do. So I don't know. Let's see. So with that all out of the way, enough introduction. Sorry, I've been doing lots of introduction in this video. Where are we at? I can't remember how I can see. 13 minutes. Okay. Not too bad. Okay. So let's actually get some code going. And I think what we're going to do to start with, a nice starting point, will be if we can make an executable that doesn't crash. I would like to be able to choose the exit code because I think that's going to be the easiest way for us to verify that our program is correct. It's a bit easier than printing values to the console. We'll do that a bit later, but I thought maybe not in this episode because because just that way we can sort of, I don't know, make a little more progress if we're not spending all our time trying to figure out how to print stuff. So that's the idea. A program that doesn't crash can give us an exit code that we supply. And then the next thing I think is to be able to assign a variable, and then we can pass that variable to the exit function. Let's see how far we get. All right, so we'll make a new, I wanted to call it Bangalang, just because I think it sounds kind of funny. And I like the idea that you're sort of like firing a shotgun or something. When you do one of these hash bangs, it's kind of like a shotgun, with all the pellets just flying everywhere. It's like all your little execution units just getting spread across the machine. Yeah, I like the name. So we'll make a source directory, and then we'll make our Odin file. Oh, Odin file. Actually, I think I remember from this project. Oh yeah, I think we can just put it in main. Let's call the package main also. So then we just need to declare a main procedure as our entry point. I try to explain some of the Odin stuff as I go. I explained a little bit in the other series, but I'm guessing there's going to be a bunch of people that didn't watch those. And hopefully this series I can up the quality a little bit of the videos. Okay, so what's the first thing we want to do is we want to read in the source file. I think we can do an import of core OS and then do, is it like read entire file? Yes, read entire file. That looks like a handy thing to do. Let's also make a directory of example programs, example 01.bang. And we just want to, to start with, we just want to exit. No, well, actually, let's start with an empty file. An empty file should be a valid program for now. It should just exit without crashing. That's all it needs to do. So let's just hard code the file for now. So what would it be? Just /examples /example01.bang. I can't remember the parameters here from file name. So there's a name. You can supply an allocator, but we don't need that. And so this is the function that we're calling, right? This is like the function signature. Well, actually, I think it's even the body of the function. And this here is how you declare multiple return values in Odin. So we're going to get an array of bytes and a success flag. So let's say source data and read OK, like that. And if not read OK, I always get mixed up with my bracket placement. It's called Allman, I think. It's a bit unpopular, but I like to have my brace on the next line. But generally at work, I follow their conventions, so a lot of the time I'm doing it on the same line. So we're just going to exit with 1, I think it's os.exit, to say, we failed, and before that, we're going to import format, which will allow us to print. And we'll just say it failed to read source file. It's like that. And then we move on to the next step. So let's get the string from the array, which I believe is as simple as string source data. Like so. Nice. So we've read our file, we've got the source. Now we want to, this part is kind of pointless at the moment because there's nothing in the file. Now we want to create an output file and we want to write stuff to it. And this part in the last series, I fumbled with for ages and I didn't even come up with a very good solution. But I did a little bit of offline investigation before starting this. So what we want to do is open the file. Let's put it in bin, out.asm. Out's not so great. Can we call it bang? Let's call it bang. Bang.asm. And then we need some flags. So we want to be able to create the file. We want to be able to write to the file. We don't need to read it. And then we also want to truncate the file. So every time we run this program, we want to start writing from the start of the file again. If there's an existing file, we don't want to append our code to the end. We just want to override everything. So that's what truncate does. And then also with this, I'm going to need to specify this little magic string. This is actually an octal, which is like, I don't know, you've probably heard of like binary, obviously, hexadecimal, decimal is 10. And this is octal, so that's base 8. And this is used here to specify 666. I'm on Linux, by the way. I'm using Ubuntu Linux. So we need to specify file permissions. And 666 means that everyone can read and write this file, which is totally fine for now. So let's say, let's call this the ASM file. I probably need to also, there's also ASM file error. This is quite often the pattern with Odin. There's multiple return values, and usually it is that the first return is the actual thing that you're looking for, and then the second one is either just a boolean to say like were we successful, or if they want to return a bit more information about what went wrong, then they return an error. I'm just going to say if it's not nil, so if there was an error returned, then we failed. I'm not going to bother doing any fancy stuff. So failed to open ASM file. So now we have an output file, and we just don't want it to crash. So we're going to just, the thing with assembly is that you need to explicitly exit the program. If you don't exit the program explicitly, then you get a segmentation fault. So we just need to write an exit. So we want to do OS, so OS write. I think, no, that's right. I think we can do format.f println. So that's file println. You can give it our ASM file and the text for the line. Let's see if I can remember this without looking stuff up. I believe we need to define an underscore start first. This is the entry point for the assembly program. So we're defining this start label, and then we have the start label. So this is saying this is the position where we start the program. And then after it, we start writing our instructions, our assembly instructions. Let's see if I can remember this syscall. So the way syscalls work, at least on Linux, it's different on different platforms, is that we need to move a few values into a few registers. And those values tell us what system call we want to call and any parameters to that system call. And then we give the syscall instruction. And then it'll execute the syscall using what we put in those registers. So I think, I want to say it's racks, good old racks. We want to move 60 into racks. So 60, let's put some comments here. That's the code for syscall exit. And then I'm probably going to have to look this up. Let's try RDI. I don't remember. RDI 0. So that's I'm guessing that RDI is the register where we put the argument 0. Argument 0 is the exit code. Let's try it. I don't know what's going to happen. And then we just call syscall. Call syscall. With a bit of luck, that should be, oh wait, I like to indent, so labels are here and then actual instructions are indented a little bit. With a little bit of luck, that should be a minimal assembly program for x86 Linux. I'm using NASM. Another thing about assembly is that depending on what assembly you use, the assembly has slightly different syntax and things. So I'm using the NASM assembler. So this should be, considering that we're on Linux, x86 is the instruction set. So that's like your Intel or your AMD chip uses those. Yeah, Linux, x86, NASM. That's the combination that I'm writing. Different combinations you'll need different assembly to a degree. Anyway, this should be the minimal running program. Another thing I just realized that I can do is up here I can defer os.close ASM file. This is another feature of Odin. So because I've got defer before this call, it means it will actually happen right at the end here. When we exit this scope, this is going to get called. So it's a little way of doing cleanup and sort of having it in the same place where you declared your, you've got access to the resource and you can have the resource cleanup right there all together. It's kind of nice. Okay. I'm a bit nervous. I don't know how well this is going to work. But let's take one of these configurations from our last project, duplicate it, and let's call this bang test 01. And we're going to need to change, we're going to need to change this folder. So we're in coding sessions, Bangalang source. I think that's what we need. We don't need any program arguments right now. And this should be Bangalang, the working directory. Yeah, so our package is here. This is where our main file is in the source directory. Our working directory is one up. Our output path is bin bang. Bangalang bin bang. See, it's a great name. Lots of fun. Okay. Run after build. So, all right, let's see what happens. Failed to read source file. So, would probably help if I spelled it right. Finished with exit code 0. So all this is doing is actually creating our assembly. So here's our assembly. It's just what we wrote in the program. It's so far extremely straightforward. This part here is the part I'm not sure about. Also define, actually. I'm not sure if that was the right keyword there. So now, if we go to bangalang/bin and we run our assembler, so we go NASM with bang.asm, and then we want to output an object file. So this is going to be the compiled file. Bang.o, is it going to work? Instruction expected. Line 1. I think this define is wrong. I'm just going to cheat a little bit and go over to this one that we previously made for the other thing. Global. I did get it wrong. It's global. This one has multiple sections. We don't need to worry about that yet. So in our main, we say global start. Run that. Bang.asm global start. Let's try and compile that. Instruction not supported in 16-bit mode. I've not seen that before. Let's cheat again. It is Rax RDI. So move Rax, move RDI. This is cool. I'm really surprised because that's exactly what we did, right? Move Rax, move RDI. This is cool. That was in our previous language, that was the halt. Core kernel, I think that's a better label. But I'm a bit surprised here. Instruction not supported in 16-bit mode. Let's just do a quick Google of that. I'm not sure why it's giving that error. Ah, yes, that's right. FALF64. So when we do the compile, we need to specify what format we're compiling to. And in Linux, it's ELF64. I don't know anything about it. That's just what it is. Okay. So now we have an object file. Great. Now we need to link that object file to make it executable. So it's a very similar command. Just go ld bang.o, and then the output of that is just, we can't say bang. Maybe I shouldn't have called all this stuff bang. Let's just call it bang2 for now. Bang2. Actually, yeah, we'll fix it up in a second. Now, we should be able to go /bang2, and we didn't get a segmentation fault. That would get printed out here if we did. So I'm happy already. And then we can go echo %? I believe that's what it is. And that's just going to print out the exit code of the previously run program, which in our case is bang2, our first assembly program. And the exit code is 0. Just to be doubly sure that that's actually what's going on, let's change it to 10. I'm going to, what am I going to do? Let's just call it out. I think that's simpler. Because our compiler is called bang. And I like having the compiler called bang, so to prevent this sort of conflicting name issue. Let's go like that. So now our assembly, we have 10 as the exit code. And then we go through our steps again. But we'll just say out and out. So we compile our assembly, looks good. And then we link like that, looks good. And then we run our executable and get the exit code, which is 10. Perfect. So we have like a minimal running program. We'll put that back to 0, and we're going to leave that. We're going to leave that at the bottom. So no matter what gets added in the middle here, if there's no explicit exit in our program, we don't want there to be a segmentation fault, so we just always have this at the bottom. It's like a catch-all exit. Cool. So now we want to actually have some code to compile. So let's say we say exit 42. So this program will give us the answer to everything. And we want to parse that. So how much complexity do we want to add right now for this simple program? Let's do some tokenization. I think we'll do tokenization. We're not really. No, wait a minute. Let's take a step back, shall we? I think we'll start doing a grammar, even at this stage. So let's make a new file, grammar.md. This is my first time doing a grammar file. I'm stealing it from this guy, Hydrogen. Well, no, that's not him. That's his project. Oros Matthew. This guy actually was the one that inspired me to even start doing these series. He has an 8-part series where he creates a compiler. This is his project on it. I think he's not doing it anymore because the last one was quite a while ago. But he wrote a grammar for it. This is a much more complex grammar than what I'm going to do. You can see here it is all here, but I'm just going to steal that so I can learn how to do this. So we want a program, which is a set of statements. And for us, a statement is, we don't want this. Okay, so we've got begin cases, end cases. Let's just cut out everything else. Probably need to end a line like this. I wonder if we can like indent this. Does that make it clearer? I think it does. And he has exit there actually. Let's just steal that. We're not going to have semicolons in our language. Well, only if we need to. My philosophy is like less is more. I don't want to have stuff if it's not really necessary. He did have actually something else that I want to steal. I probably should figure out how to do this myself, but integer literal, I think this is like a new line. There we go. Integer literal, in cases integer literal. So I guess actually we want something like this over here, which we call integer. So I should probably explain what the hell I'm doing here. So this is the grammar for the language. So the language consists of, it's a program, this is sort of our entry point, which can be one or more statements. That's what the star is, one or more. And a statement can be exit. That's like that's the only choice right now, is that it's exit. I do feel like I've not got this formatting right yet. I'll have to learn this a bit better. Yeah, it's like it's got some cases, but it's only one case. So let's just take that out for now. So actually we'll want something like this. So the only thing that a statement can be right now is an exit, which takes an integer. And an integer, I'm not even going to explain what an integer is. An integer is an integer. So this is our grammar. It's really simple. We have one or more statements where each statement is an exit command. Okay, so given that information, let's create a new file called tokens.odin. And the main thing we're going to do here is tokenize, which is a procedure which takes in a string, the source, which is actually a string slice. Oh, he puts a brackets here, doesn't he? I think. So in Odin, a slice is like a view into something, and you can often use it like, so a string itself will own its memory, and then a view into a string is just saying, hey, it's like a pointer to a portion of the string. So you can use it as a reference in a way. So I'm passing the string in by reference, because if I went like this, I would be copying it in, I think. Actually, I don't know Odin well enough. I feel like that's getting too complicated. Let's just pass in a string. Maybe it copies it. We don't care right now. And then we want to return our tokens, which I think can just be a dynamic array of strings. So this is what you would call in C++ a vector. This is a similar thing, dynamic array of strings, or in higher level languages like JavaScript, for example, that's just what an array is normally. You can just add as many things as you want to an array. You don't have to say how big it is. So we're just going to do that, and it's going to be full of our tokens. So what we want to do is have a for loop. I think I'm just going to do a traditional for loop for now. Well, I guess first we need to declare our tokens array. So that's a dynamic string, and at the end we're going to return it. Hopefully that's going to make this guy happy. Oh, file scope. That's right. I think I need to do package main. There we go. And I think, yeah, that's just like that. So if I was going to assign something to it, yeah, then it would be like this. This is how in Odin, this is how you create something. Oh no, you use curly braces. No, I've got it wrong. Compound literals of dynamic types are disabled by default, so you can't assign like this. Okay. All right. Anyway, for now we've declared tokens as a dynamic string array. So now we want to go index is 0, index is less than the length of string, index plus equals 1. Am I getting this right? Is it just commas? Or is it semicolons like this? Oh, that doesn't seem to have an error. So we're going to loop through all the characters in the input. And Odin does not support plus plus, so we have plus equals 1. Now, depending on what we get, will determine what we do. So if we find, I think there's a convenience function here. I want to say that it's in core strings. Strings.isSpace. So if our current character is white space, I don't really like this name, but it means if it is a white space character, it will return true. So if we found white space, then we just want to skip to the next thing. There's nothing to do. Do nothing. Otherwise, I'm mixing up my bracket positions. Otherwise, what else could it be in our valid program? It could be a character. Strings dot. I don't think ASCII space, delimiter, and cut sets. Yeah, they don't really have very many convenience functions like that. So I'm going to say if it is greater than or equal to a, or, well, actually, according to our grammar, there's not much that it can possibly be. It can be an opening bracket. It could be a closing bracket. That's a token. And it could be an E for exit. If we really want to follow the grammar, those are our two. Oh, and it could be numbers. Could be a number. So, and it could be a negative number. So, we'll say if it's greater than or equal to 0 and less than or equal to 9, that's a number. Or, that should be equals. If it's equal to the minus sign, dash, that's also valid. This could be an integer. So here, oh, what's wrong here? Can assign value of type U8 to rune. Do I just need to cast it or something? In Odin, the casting is quite explicit. Yeah. So quite often you need to explicitly cast things. So I don't know why the character in the string was not a rune already. It's an 8-bit unsigned integer. That's what U8 means. I don't know why that is. So, and rune is a bit of a funny word, but that's what Odin, that means char in Odin. So white space we do nothing with. If it's an open bracket, then we're going to go tokens. Oh, I think it's append. Tokens, the bracket. And I think we need to pass in a pointer to the tokens, yes. Same with the closing bracket. They're just single character tokens. Then if we find an E, we're starting an exit. So we're going to be super strict here. Actually, we might as well just do it in this initial condition. Well, we need to do this. Yeah, so we kind of need to go, kind of just say if index is less than the length of the source minus 4. If it's the length of the source minus 4, that means that there should be 4 more characters. I think it's minus 3. We can test that. I think, to make sure that's right. Let's say if it's greater, then we want to just throw an error like we did over here. We'll need to import the format stuff. Oh, we haven't imported OS either. We'll do a better job of this later, error handling. But this is good enough for now. Not enough space for exit. It's a silly error. Yeah, this tokenizer is super basic right now. It'll get much more sophisticated, but this is what it is right now. So now we've established that there's enough space for all the characters of exit. We can say if index plus 1 does not equal x, or index plus 2 does not equal I, or index plus 3 does not equal t, then we didn't spell exit, did we? Yeah, that's how you spell exit. And if you spelled it wrong, then that's too bad. You're not a valid program. You spelled exit wrong, you dummy. Okay. So, assuming that they spelled exit correctly, we will add the token exit. And we will also need to advance this to go past all these characters. It automatically will advance past the E here, but we wanted to advance past all these as well. So let's go plus equals 3. Like that. And now the number. So now we're going to say, well, let's save the start index. And I've done it wrong. Oh, declared but not used. Yeah, that's fine. And then we'll say for, everything is for in Odin. There's no while loop. So this is a for loop that's going to look like a while loop. So for yeah, as long as it's a number, this can only be at the start, the minus. As long as it's a number, we're only dealing with integers right now, so we're not going to include the decimal. I was going to say, what about other locales where they use commas instead of decimals? But I think in source code that's not valid. I think it's just decimal, thank God. I mean, just a period. But anyway, we're not doing floating point numbers yet. That is one of the features I want to support, but kind of early on, but not yet. So as long as we do that, then let's keep incrementing the index, right? So then at the end of this loop, the start index will be where the first character is, and index will be where the last valid character is. So our token is going to be a slice of source. So this is where we get into our slices between our start index and index plus 1. So maybe this is kind of obvious syntax. I think it's a nice syntax. So we're taking source, and then we're taking a slice of it, starting from the start index, going to index +1, exclusive, like these operations normally are in programming. You include this one, you exclude this one, which is why I'm doing +1, because we only incremented when we found a valid character. But we didn't increment after we found this valid character. So yeah, so this increment is kind of incrementing us. Oh, wait a minute. So this first check is still looking at this index, which could have been a minus, and then it would fail straight away. Let me walk through this. It would fail straight away, in which case start index, end index would be the same. But because we do index +1, this slice is going to be one character, which could be just the minus sign. Just the minus sign is not a valid character, a valid number. That's an interesting edge case. I didn't think about that before. I think our indexes are correct, but I'm going to, for that edge case, which I would not have thought of before, I'm going to say if the first character was a minus and no, this is not right, because if we found a minus and then we check that same index for a number, it's going to fail. It's never going to find numbers past the index. So I think we're going to have to do this to go to the next character. Then we check if that's a real one, and if we do, then we go past it. So we're always going past. So this, yeah. So index is always one past where we've found a valid character. So we can just put it here without a +1. But I still want to handle this edge case. If we found a negative sign at the start and index equals start index +1, that means we didn't find any valid characters after the minus sign, then that's invalid. Negative what though? Like negative? Negative because we're nagging them that they fucked up? Negative what though? Yeah. What's my confidence factor that this is actually going to work? I'm feeling pretty good about this. I'm going to give it 85%. 85% that it works out the gate. Let's see what happens. So we can do print. I forget if you can just do, like, if I can just do print line and then tokenize source. Can I just do that? And that's going to, oh no, I didn't need to add an import for that because it's in the same, with Odin, if you're in the same folder, you're considered to be in the same package. I'm not sure why you need to have this package thing as well, but you're considered to be in the same package, so anything declared here is available here, unless I don't know. I think there is some way to hide it. By default, it's public. So let's see if we get a list of tokens. Huh? exit bracket 42. That's a pretty good start. We missed our closing bracket. There is a closing bracket, isn't there? Yes. Okay, so yeah, I was 85% confident, and I feel like that was like 85% of it got passed right. Exit bracket 42, closing bracket, so it's a token. So I think somewhere we're stepping, when we parse our number, are we stepping too far? Because when we parse our number, we're always stepping past, yeah, we're always stepping past the value we just checked. So we're always going to step to a character past the number, and then when we get to the top of the loop, we're going to step even further. So I'm not sure how clear that is. So with the number 42, we come into here with the first one, and we see, oh yeah, 4 is between 0 and 9. So let's increment that index. So now the index is pointing to the 2. And then we go, okay, do we find another number here at this current index? And 2 is between 0 and 9. So yeah, we found another number. So let's step ahead again. Now we're on the closing bracket. So we come to this loop again. It's not between 0 and 9. So we're done here. We didn't hit this edge case. So we add our token. The token's correct. And then we come up here and we step forward again. And now this is false, and we don't get our bracket. So our logic in here is not fantastic. What's the nicest way to do this? Maybe we can do like a start index and an end index. End index being index plus 1. And we keep, I guess we're going to be checking that like that. And we append with the end index 2. Yeah, so we use our end index the way we were using index before. And now at the end, we say index is end index minus 1. Oh, we're not reassigned. This is creating a new variable. I like that it changes the color actually. This is the colon equals is like declaration assignment, and you can also optionally put a type here. If you want to explicitly type this. But equals is just an assignment of an existing. Okay, so this I don't want to allow in my language. See, because I nearly got that wrong. In my language, if you tried to declare a variable here with the same name as what's declared up here, I want it to be an error. I don't want it to be possible. It's called shadowing, and I don't like it. I just feel like it's an opportunity for a bug, and just find a new name for your variable. It's not that hard. So, yeah. Yeah, so now I think we're effectively making the index 1 less than what we had it before. So let's try running that again. Boom, nice. Okay, so we have our tokens. Now we go here and we see a program is one or more statement. A statement must be exit bracket number bracket. So I think we're just going to say for token in tokens, I think it is. For token in, oh, we don't have our tokens. Tokens is the result of tokenize. We don't need to print that out. Should we do this file stuff first? I think that's a good idea because we don't want to go through the trouble of making all our tokens just to find that we can't even write a file out. I think it's better to fail early. So we're going to loop through our tokens. Do we want to? Okay, let's make a new file. Parsing.odin and parse program. And that's going to be a slice of strings. Oh, we need to do our package. Parse our program, and that's going to have this loop in it for token. And actually, it's more going to be like a traditional loop. You know what? Actually, I'm going to skip this for now because I noticed we're over an hour already, and I want to keep these videos not too long. So what I'm going to just say is I'm going to put this here. And for now, I'm just going to say the program is only valid with a single exit statement. Not one or more, just a single one. So if tokens 0 equals exit and tokens 1 equals bracket and tokens 3 equals close bracket, then we've got an exit call. Then we've got an exit call. And in that case, we just print out our exit, right? And we want to use printf line so that we can put an integer here and that, oh no, it'll be a string. Put a string here and that's going to be tokens 2. So yeah, whatever number we had in tokens 2 will get printed here. Yeah, sorry, I feel like we're kind of like, it's a little bit weird to just do one, you know, like not to have a loop, because we've already established the grammar as one or more statement, and now we're just saying you can have an exit command and that's it. But one exit command. But next time we'll get a bit more time to do that. We'll do that properly and we'll get assignment going at least. So now, yeah, we see we've got an exit call, we've got 2 exit calls, and this one is 42. And if we change it to 43 here, and we run again, then we have an exit call of 43. So it's really quite basic what we've done so far. We've done the beginnings of tokenization. We're able to split our program into tokens. I'm actually going to add an else. Else unrecognized token. So then, so yeah, we just got a simple tokenizer and a simple parser that just looks for an exit statement and at the start of the file, and if it finds one, then it prints an exit. And we can confirm if we go through our steps from before, compile, link, run, check exit code, we get 43. So we're all good. One last little thing we can do. Sorry, we're at an hour 10 already, but I did want to, because we did build into this tokenizer some checks here. I kind of just wanted to make sure that it does handle some cases, if we do some things wrong. So like if I put exit, it says you spelled exit wrong, you dummy, which is nice. If I put 43 FTZ, so that's not a number. It says unrecognized token because it tried to find a number and it couldn't find one. So actually that also makes me think, I guess, yeah, I think we could have a few issues with this implementation because it went through trying to look for numbers. Oh no. No, I think it would have found the number token properly and it would have established that 43 is a number and then would have looked for the next token and it found FTZ and it said, what the hell is that? If we say negative 43, it should pass, even though you can't exit with a negative code. So it's probably just going to wrap around or something. And also exit codes can only be up to like 128 or so. I'm not sure exactly what it would do. Okay, I think that's the beginnings, the very bare bones of our language. And hopefully next session we can get into something a little more meaty. We can do like a assignment of variables, which will be interesting because then, we need to store things on the stack and then we need to be able to reference them later. And yeah, I think that'll be fun. So, thanks for stopping by. Hope you enjoyed. If you did enjoy it, if this seems like a series that you would like me to continue, you can give the video a like and then I can just gauge how much people are enjoying the series and I can continue it. Otherwise, I can move on to a different project. Yeah. Or please, if you have something you want to suggest or something, I love it. I love getting comments, so leave a comment. But yeah, until next time. Ciao.